In machine learning research, one very interesting and important research topic is how to optimize our parameter in a distributed computing environment. Okay, so up to now we have discussed many optimization techniques where we basically use a single machine. So one computing machine can control every parameters. So we usually update every parameter simultaneously. Or in coordinate descent approach, we update parameter one by one at each time. But still, we don't need any communication between different machines. Okay, so basically we consider an objective function with respect to parameters. Usually the zeta is a vector, so a bunch of different parameters we have to optimize. But we usually have many data points, and each data point defines different functions. So this is one typical notation where we have to find the zeta star that minimize f zeta. Okay, so that is one possible notation. Or in some case, in some papers, we also use this notation. There is some loss function, and the loss function depends on some random variable zi, and usually this gi indicate our input and output pair of data. Okay, so that is also a very common expression of our machine learning problem. We usually utilize first order method, so we compute the gradient vector at each time, and then using this gradient vector we update parameters. So every time we compute the gradient of f zeta t and update zeta t plus 1 using zeta t minus step size gradient f zeta t. When we cannot compute the full gradient, we have to use stochastic gradient called GT, and using stochastic gradient we learn stochastic gradient descent algorithm to optimize your parameter. Okay, so that is a typical machine learning process, especially for deep neural network. When we can utilize multiple different machines simultaneously, we can implement such optimization process in distributed manner. So, for instance, in this case, we have three different machines, machine 1, machine 2, and machine 3, and each machine contains CPU and GPU. So basically using these different machines, we can speed up their learning process. One possible distributed system is just split the data set. So basically in the classical setting, original setting, we have data point x1, y1 up to xn, yn. So to compute the full gradient, we have to compute the gradient of each data point, so that require n different computations. And because this is too heavy computation, we usually randomly sample mini batch and then estimate the full batch gradient using the mini batch. That is called stochastic gradient or mini batch gradient. When we have many different machines, we simply split the entire data set into several disjoint pieces, or it is allowed in some case some overlap between different sub data set. Anyway, when we have multiple different servers, we can split the entire dataset into multiple pieces, and each computing machine estimate the full batch gradient only based on the subset located to the machine. Okay, so for instance, when we estimate the full batch gradient using 16 data points, machine 1, machine 2, and machine 3, we can estimate the gradient using 16 times 3 number of data points. Because we can compute the gradient for 16 data points at each machine. So at the same time, we can compute 16 by 3 different data point gradients. Okay, so that's one very nice property of distributed system. But to combine this information, the gradient information, we have to communicate the information between the servers, right? The estimated gradient from this side, the estimated gradient from this side, the estimated gradient from this side should be averaged so that the entire information can be combined. But the problem is the gradient require a lot of message space, a huge message space. For instance, in a deep neural network. In deep neural network, we have a lot of parameters, and each parameter should define partial derivative. In gradient, every single parameter have to define or have to compute the partial derivative. So if we have millions different parameters, then the gradient dimension is million. And to communicate the gradient information, we have to convey full million dimension vector that require a huge message. So one main bottleneck for distributed system setting is communication cost. We have to communicate a very huge size of data every iteration. Okay? So from now on, I will introduce how to reduce such a message size, or how to make the message passing frequency more rarely. So currently we are considering the gradient descent algorithm. At every gradient update, we have to communicate all the information, but it is possible to make a system that communicate every 10 iteration or every 20 iteration. So during 9 or 19 times, we never communicate, just update locally, and then communicate just very rarely based on the local updated information. That is called local SGD, and I will explain what is the convergence behavior under that scenario. Okay. There are many applications. One is just data center scenario. Another one is federated learning. So what is federated learning? So basically every day, every life, we now live with smartphone. We always use some smart devices like Android phone, iPhone, or iPad, or laptop. And each smart devices usually contain very personal information. And this personal information also very nice source to provide personalized service, recommendations, and some very nice convenience thing are usually based on personal information. But the personal information is very sensitive data, so it has privacy issue. So usually we cannot send our privacy information, the personal information, to the main service center. Right. So in many scenarios, we have to train our neural network model or machine learning model in distributed manner, because data is located in many different devices. And we have to combine these information so that we can get more accurate service. Okay, that is why we have to study distributed learning. And especially in this personal devices scenario, we also consider privacy issue and some, differential privacy algorithms kind of things. And that is actually out of scope of this course, but they are also very important research topic in machine learning. Okay, so I want to first introduce TONGRAD. TONGRAD is a gradient compression technique. So the scenario is very simple. There is one center parameter server, and there are many different worker nodes, and worker node is not center parameter server. They just locally compute their gradient and send the gradient information to parameter server. Okay, and parameter server just combine all the information and send back to each worker the averaged gradient. Okay, since each worker contains different data point, their estimated gradient only contain their local information, but after averaging, the gradient information contain whole data, right? And so the gradient direction now is good for everyone. Right, so for this scenario, one bottleneck is communication. Every iteration, each worker have to compute gradient, and then they have to send the information, gradient information, to the main server. So if we use floating point variable to store its partial derivative, if you have 10 million parameters, then you have to need 10 million times 32, 10 million times 32 or 64 bits. Okay. Why? Because floating point require this amount of number of bits. So one possible compression technique for this huge message is quantization. So instead of using such floating point variable, we can use integer variable with 8 bits or 16 bits. Okay, since the number of bits decrease compared to the original case, the total information we send is smaller than the original message information. But this quantization still good. Already we have 10 million different information, and because of this huge information, we already have nice direction to decrease the loss function. So still it's good. Okay, and we just need to make a stochastic gradient concept. Still have the which expectation equal to the original gradient. So we just need to keep this one. The expectation of gradient equal to gradient of full loss function. Okay. So to make such stochastic gradient, even with quantization technique, this paper introduced tunnelized operation, and this tunnelized information is it's not special. It's very simple. Just make a 0 or 1 information using some stochastic process. So with probability st over gt absolute value, we set equal to 1. With probability 1 minus gt over st, we set value equal to 0. Okay, so this is very extreme case. And then keep the sign, and then keep the ST value. ST value is defined as like this: maximum value of absolute value of gradient vector. So if you have this gradient vector 0 0.1, 0 0.6, minus 0 0.5, 0 0.3, then ST is equal to 0 0.6. And each probability compute, for instance, this case, 1 over 6, 5 over 6. For this, 1 and 0. For this, 5 over 6, 1 over 6, and so on. Okay? Okay, then when you take the expectation to G tilde T, you can easily check this. Expectation of G tilde T is equal to GT. And usually GT is very nice stochastic gradient. So when you take expectation with respect to the randomness of GT, you have gradient of F zeta. Okay, that we want. So G tilde T is still a stochastic gradient, and of which expectation value is equal to the original full batch gradient. So G tilde T is unbiased stochastic gradient. Okay, so that is very nice. And this is very extreme case. We set every element as Boolean variable, so just 0 or 1. So 1 bit is required to store each element of gradient vector. But we can extend this this idea to 8-bit scenario and 16-bit scenario. So we just quantize the space from st to minus st, and then just compute the probabilities so that your original value becomes the expectation. Okay. QSGD is almost like Tongrat. Just a little details are different. So QSGD also use the idea, the quantization technique, where the random stochastic rounding is applied. So the stochastic rounding means we make the continuous real value to be quantized discrete value, but with a stochastic assignment, we make the expectation of quantized vector becomes equal to the original vector. Okay, so when you go to the QSGD paper, you can find this equation and more detailed expression. And this explains why such quantized stochastic rounding keep the same expectation.